What's up about penguins? Today we look at Hardy-Weinberg. We're looking at a slightly different way to solve it. I call this the counting alleles method. And this is going to be used when you have a question that you know the number of individuals that are of each different genotype. So before we get into the formula, which I do have the formulas at the bottom corner, let's talk about the actual variables that we have here. So P would be the frequency of allele 1, which I'm going to call dominant. And then Q is going to be the frequency of allele 2, which I'm going to call recessive. AA would be the number of individuals that are homozygous for allele 1 or are homozygous dominant. And then P squared would just be the frequency of those individuals. AA, or lowercase a, will be the number of individuals that are homozygous for allele 2 or are homozygous recessive, with Q squared being the frequency of being homozygous allele 2, so homozygous recessive. And then A little a would be our number of individuals that are heterozygous for allele 1 and 2. And again, 2PQ would be that frequency. So when we're solving this problem, I want to know the frequency of being homozygous dominant. I take the number of individuals that are homozygous dominant divided by the total number of individuals. 2PQ would be the number that are heterozygous over the total, and Q squared would be the number of individuals that are homozygous recessive over the total. And again, that's giving us those frequencies. If I wanted to know the frequency of the dominant allele or a frequency of allele 1, I'm going to say 2 times the number of individuals that are homozygous dominant because they have 2 dominant alleles. Plus, I'm going to add the number of individuals that are heterozygous because they have 1 of those dominant alleles. And I'm going to divide by the total times 2 because each individual has 2 alleles. And the same I'm going to do for my frequency of my recessive allele. 2 times my homozygous recessive because homozygous recessive has 2 recessive alleles, plus 1 of my heterozygous because of the fact that those are going to have 1 of those recessive alleles divided by the total individuals times 2. So a cruise ship is stranded on Desert Island. There's 400 individuals aboard. There are 200 individuals with sickle cell trait, so those will be carriers, and 150 that are unaffected, and 50 individuals that are sickle cell disease or homozygous recessive. So my P squared, or my frequency of homozygous dominant, is going to be the 150 unaffected individuals divided by the total individuals, which is 400, which gives me 0.375. 2PQ is going to be the number of individuals that are heterozygous. We know they're heterozygous because they're carriers for that trait. So 200 divided by 400 gives me 0.5. And then my Q squared would be the number of individuals that are homozygous recessive divided by 400 being our total, give me 0.25. So now comes that counting alleles that I was mentioning before. Now this formula, again, it's sort of made up. So if I'm going to use this, I'm going to say 2 times the number that are homozygous dominant. So homozygous dominant was 150. So 2 times 150 plus I'm going to do 1 times the number that are heterozygous. So that was 200. And I'm going to divide by the total individuals, 400 times 2. So 2 times 150 gives me 300. 1 times 200 gives me 200. Divided by 400 times 2 gives me 800. If I do 300 plus 200, that gives me 500. And divided by 800 gives me 0.625. Now, you could go ahead and say 1 minus 0.625 to get your Q because now the Hardy-Weinberg equilibrium formulas we learned last time will work once you've counted one of them. But just to make sure that you didn't make a math error, I would solve for the other one. So Q is going to be the number of individuals that are homozygous recessive times 2, plus the number of individuals that are heterozygous divided by my total times 2. So that'd be 2 times 50 because 50 individuals are homozygous recessive, plus 1 times 200 because 200 individuals are carriers, divided by 400, our total population, times 2. 2 times 50 is 100, 1 times 200 is 200, 400 times 2 is 800, so 100 plus 200 gives me 300, divided by 800 give me 0.375, and to confirm that I did the math right, if I was to add 0.65 plus 0.375, I would get 1, which is what we should find. So go ahead and pause the video and see if you can solve this problem. In this one, I've actually, instead of it being a dominant and a recessive, we're looking at codominant because of the fact that they're A and B alleles. But go ahead and solve this and see what you can do. So for this problem, we're going to know that in a given population, only A and B alleles are present in the ABO system. There's no individuals that are type O, which tells you that there's no individuals that are homozygous recessive. So if 200 individuals are type A blood, that means that they are AA. And then 75 are type AB, so they're going to have 1 A allele, 1 B allele. And 25 are type B, so they're going to be BB. What are the allelic frequencies of this population? AKA, what are the P's and the Q's? So just that we were going over the same formula we did before, I did solve the P squared, the 2PQ, and the Q squared. So P squared is going to be 200 divided by 300 because two individuals were AA. Over the total of 300, give me 0.667. 2PQ is the 75 that were AB. Over the total of 300, give me 0.25. And Q squared was 25 individuals that were BB over the total individuals of 300, give me 0.083. So the same thing when I solve for my P, I'm going to do 2 times the number of individuals that are homozygous dominant. So 2 times the type A plus the number that are heterozygous, so AB, and that would give me 400 because 2 times 200 is 400. 1 times 75 is 75 divided by 600. And then I add those together, gave me 475 divided by 600, give me 0.792. To find my Q, I would do the same thing, but instead of doing homozygous recessive, now I'm just looking at homozygous for the B allele or the second allele. So 2 times the number of individuals that are BB plus the individuals that are heterozygous or having A and B. That gives me 50 plus 75 divided by 600. So 125 divided by 600 gives me 0.208. Hope this was helpful. Remember, API pain was just assessed by all.